A bit of a, okay, that should be fine. Sorry, I had a bit of technical difficulty accepting the recording, but I think it's working now.
So it's all set on my side. Do your slides work to change them?
Yeah, they work.
Yeah, all right. Good. Okay, so we're ready to go. Thank you all for joining. Thank you, Alexander, for accepting the invitation. Today's QISS seminar is on John Wheeler and quantum gravity. Alexander Blum is from the Max Planck Institute for the History of Science in Berlin and the Albert Einstein Institute in Potsdam. So today's seminar is on the history of science, which is the first such seminar we have in this series. So I'm very excited about it and looking forward to listening what Alexander has to say. Whenever you're ready, Alexander.
Yes, thank you very much. Thank you for the invitation. It's a pleasure to be here. It's always fun to give talks to physicists where you don't have to start with a slide explaining what quantum gravity is and why it's important. So we can go right at it. Right, I'm going to be talking, as Mario said, on John Wheeler and quantum gravity, and that is not just a random choice of somebody I happen to be working on. But clearly, John Wheeler plays a very important role in the history of quantum gravity. And as I'm going to argue in this talk, he's especially important for shaping a vision of what quantum gravity is and should be, and of its importance within the structure of physics more generally. So instead of starting with a slide that impresses on you the importance of quantum gravity in contemporary physics, which I'm sure you're all aware of, I'm going to start instead with a slide with a quote that I often like to flash in situations like this, to impress on you how little of a concern quantum gravity was for physicists early in the 20th century. So this is a quote. It's hard to even find quotes, and there's like a handful of papers early on. But it's a very marginal problem. I think this quote makes it clear. It's a quote from a paper by Werner Heisenberg and Wolfgang Pauli, two of the pioneers in the construction of quantum mechanics in the mid-1920s. And in the late 1920s, 1929, they write the first paper on quantum electrodynamics, on really a quantization of Maxwell's theory using the quantization procedure developed for mechanics. And in that paper, they have like this short side remark on the quantization of gravity, remarking that they further note that a quantization of the gravitational field, which appears to be necessary for physical reasons, should be possible without new difficulties, using a formalism entirely equivalent to the one used here. And that's all they have to say to that. And of course, they have a lot of difficulties with quantum electrodynamics. So it's not like they're saying, we could do this in a week's time. But it's a side problem, right? It's not something that they feel is very, very pressing or like a central concern for fundamental physics, but just something that appears to be necessary for physical reasons. And so the question then, the historical question, the question for the historian is, what made quantum gravity the central problem that it is today? On the one hand, of course, it's the appearance of unprecedented technical difficulties, right? As opposed to what Heisenberg and Pauli was saying, fixing the problems of quantum electrodynamics through renormalization turned out to be a lot easier than constructing a quantum theory of gravity. And that fact, among others, made it appear to be like the last remaining problem in fundamental physics. The last big microscopic frontier for an extension of a quantum theoretical view of the world after the completion of the standard model of particle physics in the 1970s and the establishment of quantum field theories, not just of electrodynamics, as Heisenberg and Pauli have been doing, but also of the nuclear forces. And so because for these reasons, it became kind of the last element that would be needed to complete a theory of everything. But of course, it's more than just a last element in the theory of everything, like the one missing piece to also get gravity into the purview of a quantum theoretical description of the world. It's much more strongly became a key element in the theory of everything, right? Even the foundation on which a theory of everything would rest, right? It's not just like the last thing we need to do on our to-do list, and that's kind of accidental that it got left over and that it's so difficult, but it really became essential to ideas of the structure of space-time and of unification. And this idea of quantum gravity as a key element is, of course, very prominent in contemporary approaches since about the 1970s and after the completion of the standard model of physics, and then also advances within general relativity. But this view of quantum gravity as a key element of a theory of everything really draws on a long tradition. And that tradition, unsurprisingly, goes back, as I will argue here, to John Wheeler, who I think is probably the most important physicist to really envision quantum gravity as the potential key to a theory of everything. So here he is in younger years, John Wheeler, born in 1911. He started his career in physics as a nuclear physicist in the 1930s, is famous for a paper that basically invents the idea of an S matrix. But what really made him very famous then was a paper that he wrote in 1939 with Niels Bohr, giving an explanation or a mechanism for the process of nuclear fission. He then also, as a nuclear physicist, worked both on the atomic bomb, in the Manhattan Project, working on reactor design there, and then also later in the 1950s was one of the prominent members of the hydrogen bomb project. He was a professor at Princeton for most of his life, beginning in 1938, and that's going to be important for our story because he overlaps with some people at Princeton whom he talks to, most notably Einstein. He is also famous for really founding a huge school, having supervised 46 PhD students, many of them as part of what would become known as the Renaissance of relativity or general relativity in the 1950s, that turned that theory from a rather marginal mathematical topic into a dynamical physical research field. And of course, the importance that he ascribes to quantum gravity is part of this also return to general relativity more widely. Later in life, he was also then known for many original and speculative ideas, starting in the 1970s, ideas like the participatory universe, law without law, or it from bit. And these gave him in the physics community like this the status of an inventor of like insightful and speculative, but also the crazy ideas. But we're going to go back before this period of the later Wheeler, where he may have been at his most famous, and go back to the very young Wheeler all the way into the 1930s. And maybe the best way, because that's we need to start there to understand how he came to quantum gravity, and ultimately then at the end of our story. So we're going to be following Wheeler's trajectory with quantum gravity, starting out with his ambitions in the early 1930s, and then all the way to kind of the end of his work on quantum gravity proper in the 1970s. And when we go back all the way to the 1930s, I think a good way to introduce that is this quote here by Feynman, who supposedly, I think it's Kip Thorne who reports this, remarks that some people think Wheeler's gotten crazy in his later years, but he's always been crazy. And so Feynman was, of course, Wheeler's PhD student in the 1940s. So he was part of this early craziness, which we're going to talk about. This early craziness is can be encapsulated as really an obsession of Wheeler with reduction, of the reduction of physics to ideally just one or two fundamental constituents and laws from which everything can be then reproduced and constructed. I mean, this is, of course, a large theme in physics more generally, but I think Wheeler, as we'll see in a moment when looking at his concrete vision, was very strongly inclined towards this kind of radically reductionist thinking. I think it should be remarked that this was, of course, also enforced by, let's say, widely political developments. Because this view of reductionism, which he pursued already in the 30s, but then also, after World War II very, very strongly, was not just like an apolitical philosophical preference, but after the discovery or after the construction of the atomic bomb, believing in reductionism and pursuing strongly reductionist physics was for Wheeler also part of the rationality of national security. Wheeler was a foreign policy hawk. That's for sure. He was very outspoken about this, also because he very strongly believed that his brother, who had fallen in World War II in 1944, could have been saved if they, at the Manhattan Project, had gotten the atomic bomb a year earlier. So just to impress on you, here's a quote from a programmatic talk that he gives in the after World War II in 1945 at a symposium on physics after the atomic bomb. And he says here that we are concerned here, this is a program that he wants to pursue, with the question of ultranucleonic transformations, in which the neutrons and protons are reduced to lower entities or altogether destroyed. So he's talking about making use not just of nuclear binding energy, as one had done in the atomic bomb, but also the nucleonic binding energy. And he impresses on his listeners that the discovery how to release the untapped energy on a reasonable scale might completely alter our economy and the basis of our military security. Other nations have not neglected this work during the war. We must prepare to resume it vigorously. And so while he felt that a lot of the nuclear physicists at the time were not really doing that, right? They were building new accelerators and discovering lots of new particles and accepting all of these particles as fundamental, and some of them even arguing that composite particle is not really something we should be thinking about, like everything is made of everything. There's then in the 60s like slogans of nuclear democracy floating about, and that's not at all what Wheeler was after. He was looking for the one constituent to which you could reduce everything and ideally also use that to release the binding energy. Okay. Now let's get more concretely to the physics. Originally, and this probably goes back to the 1930s, though we really only have evidence for it then starting in the 1940s, Wheeler's idea was what he called in one of his typical catchy slogans, though also only in hindsight, everything has electrons. So his idea was that wouldn't it be possible maybe to reduce all of physics, and that mainly meant nuclear physics at the time, because that was the frontier, everything to electrons. Could we maybe manage to explain the entire structure of the nucleus and of nuclear forces through electrons? So here's a letter that he writes to Niels Bohr about this. And he's very anxious to get his opinion. He writes on the question, is it possible to exclude a picture of elementary particles, of elementary particle constitution, based entirely on positive and negative electrons? It seems to me that the crucial issue is the one of spin and statistics, and that one can at least imagine ways out of all the other difficulties. So this is really, it's a very specific program, not just of being reductionist, but actually saying, can we build everything from electrons? And he writes to Bohr, though I joke with you about my heresies, I am trying to be just as honest and as open as I can about the elementary particle problem. That's what he called this idea of finding the fundamental constituents. I know there's no one who has your insight. And then he wants to talk to Bohr about these things. Now, these are ideas that he nurses mainly in private, but one can understand some of his work in this light. In particular, two famous papers that he writes with his PhD student, Richard Feynman, in the 1940s. They were written early but published in 45 and 49 on what's now called Wheeler-Feynman electrodynamics, which is a theory of electrodynamics and the electrodynamic interactions of charged particles that eliminates the field, right? There's just advanced and retarded interactions between the electrons. There's no field involved. And this is actually, though it's not stated in the paper, very clearly part of Wheeler's vision of everything as electrons, where you even get rid of the electromagnetic field and just have electrons interacting through direct advance and retarded interactions. And his hope was that, in general, this would be equivalent to electrodynamics. But you might actually, in confined spaces like nuclei, maybe actually get deviations from electrodynamics. And you can find hints at that hope in the paper. So this is kind of the starting point, right? And there's no general relativity here yet. So we'll see how he gets to that and to quantum gravity in what follows. So like I said, these papers, the first paper was published in 1945, but was completed already, or the work was done earlier when Feynman was Wheeler's PhD student in the early 1940s. And there in 1941, Feynman gave a seminar on this, presenting their ideas on direct action at a distance theories between electrons. And so this was at Princeton. I mentioned, this was, of course, certainly the place to be for physics in the 1940s. And so in the audience of Feynman as a young graduate student, there were these two gentlemen here, Einstein and Pauli. And they both asked a question, right? Einstein asked the question, or rather made the remark, he didn't think that one could do this action at a distance business also for general relativity, or could one? While Pauli asked, how will one quantize such a theory? And in a way, then Wheeler and Feynman went off in different directions. Feynman pursued the question of quantization, and in the course of that, developed his path-integral approach. While it was Wheeler who got intrigued by the question of whether one could do this action at a distance also for general relativity or for gravitation. So the idea was originally maybe one could not just get rid of the electromagnetic field, but even of the space and time in which the electrons are moving and the gravitational interaction, and get all of that also through action at a distance, as one does for electrodynamics in Wheeler-Feynman theory. So we should be, and at this point, I should mention a bit about what Einstein was doing at that point in time, because this becomes important then also for the way that Wheeler thinks about addressing Einstein's suggestion of expanding the action at a distance approach to general relativity. So Einstein, this is of course many decades, 25 years about after his completion of general relativity. Einstein has moved on and is now doing what would be called his unified field theory. And so it's one can see the affinity with what Wheeler was thinking about, this reductionist idea of finding the fundamental constituents, and ideally just one, because Einstein too was interested in the constitution of elementary particles, but not through electrons, obviously, but through curved spacetime, or through fields more generally, through a continuous field that you would somehow get elementary particles as localized bunches of energies in a field. There were lots of problems, obviously, in Einstein's program. One of them was the problem of how these entities would be stable, right? How you get stable elementary particles out of this. And of course, Einstein famously rejected quantum mechanics. So he did not, this was not a quantum field theory he was talking about. He was talking about a classical field theory from which he wanted to get particles as localized excitations of the field. And the hope was that somehow quantum mechanics would drop out of that, right? That the particles thus constructed, which weren't Newtonian billiard balls, but somehow twists in the field, that they would somehow also obey the laws of quantum mechanics, and thus make quantum mechanics not like a fundamental theory of probabilities in Hilbert space, but kind of like a corollary of this unified field theory. And then he was not working in the context I was talking about, like it's a continuous field, but he was working on the idea of unifying gravitation and electrodynamics as the field that would then form the substratum for all of these particles. And that was actually the main focus of the research, was constructing such a field theory. While the ideas about constructing particles from this was more like a programmatic promissory thought, but still there was this connection of the problem of elementary particle constitution that connected his work with Wheeler's. But by the 1950s, I've written here, but actually already earlier, this was not considered, people had already kind of resigned themselves to the fact this is like the later Einstein would not be living up to his glory days of special and general relativity. So that's what Einstein was doing at the time. We'll get back to that in a moment. What he was doing at the time when at Feynman's seminar, he asked, could we also do action at a distance for general relativity, gravitation? So Wheeler's intrigued right away. He writes a letter to Einstein, still during the war. Einstein and Wheeler, both of them are doing war work. Einstein is working for the Navy. Wheeler is working in the Manhattan Project. Wheeler writes him a letter. He would very much like to visit Einstein and see if you can't help me better to see where the force of gravitation fits into the point of view of the theory I have mentioned. So this action at distance. It will be convenient for you to see me some Sunday afternoon, either in Princeton or in Aberdeen, where I believe you are now. That would be wonderful. And so he meets with Einstein, and they start talking, and Wheeler actually starts developing ideas on gravitational action at a distance. He starts in the 40s, but of course he gets, the war work keeps him, and then he's also working on the hydrogen bomb after the war. So he really gets into this program of action at a distance gravity and eliminating not just the electromagnetic field, but also the gravitational field, and really just having a universe of particles, as he sometimes also calls it. He starts working on that in the 1950s, and that's part of his also public engagement with general relativity, which becomes important for bringing this theory from the mathematical backwaters to the active physics community of the United States. So he starts with this idea, right? Which I don't have a pointer here, but so on the upper left-hand corner, you can see his idea is to somehow just have world lines here of electrons, and then we somehow would be able to reconstruct all of general relativity and all of space-time by what is here called associators. Back then, he actually called them liaisons. This is from a later paper. So basically, the light cones connecting points on different world lines, and from all of the different light cones and relations between them, you would somehow be able to reconstruct space-time, or get gravitational interaction. He explored this for a while, but it doesn't come very far, right? I should mention here the reason why we can really, starting at this point, follow his research and his thinking very closely is because we actually have access to his notebooks, and he kept very detailed notebooks. So we'll be seeing quite a few snippets from these notebooks. And here's the first one at the bottom of the page, where he ultimately resigned himself to saying, well, that deduction of, in this case, the Hilbert action from these kinds of liaisons between world lines without like an underlying space will come later, we hope, and from some action principle. And then we'll have to assure that the description is approximately embeddable in a Riemann 3+1 space. So that's, he realizes he's not going to be able to do proper action at a distance gravity. He puts that as a program for the future, and this picture here with the associators is actually from a paper he then wrote very late in life in 2003. All he could get was to get motion of particles in a Riemann space already assumed to exist. Okay, so he gives up on the hope of eliminating space and time entirely, and instead starts thinking about his particles as singular lines in an already existing space-time, because he's very impressed by the results of Einstein and Infeld and Hoffman, that you can to some extent derive the equations of motion of such singular lines from the field equations. So it still seems to him that that's kind of the thing he then looks into, and so he has like seems to be giving up on the everything is electrons. Now there are both world lines and fields, but they're very intimately connected. But as we follow him further, he goes a step further and actually goes in the very strongly in the direction that Einstein was pursuing. That's no chance, right? They were that's not by chance. They were talking. Einstein would regularly visit Einstein. Wheeler would regularly visit Einstein at his house and take his graduate classes there to visit Einstein. And so in early 1954, Wheeler comes up with an idea of his own of actually constructing particles not as singular lines within a space-time. So first it was singular lines without a space-time that somehow reconstruct a space-time by themselves. Then it was singular lines in a space-time. And then he finally, after some back and forth, and we can follow all of the details in his notebook, reaches the Einstein point of view. Maybe we'll just have particles made out of space-time, just as somehow localized field energy. So here's the first entrance in his notebook on that at the top of the page from January 54 in Rochester. He mentions the Kugelblitz, which would later become known as a geon, a ball of light held together by gravitational forces, as a classical model for an elementary particle, fireball, or as Arthur Whiteman suggested to him, Kugelblitz. So at this point, Wheeler has reached, has kind of at the beginning, they just had, Wheeler and Einstein had like a similar view on reducing elementary particles to some underlying structure. Now they've actually converged. They both want to construct elementary particles just based on curved spacetime, on a continuous field. Wheeler, of course, comes up with some new flashy names. He calls them geons, gravitational electromagnetic entities, and he also coins the term of wormholes once you use topology, which we'll get to in a moment. But the big difference between him and Einstein is that Wheeler is, of course, not a disbeliever in quantum mechanics. He's very happy to accept quantum mechanics as one of the principles he's working with, along with general relativity. Because that also solves basically all of Einstein's problems. It obviously solves the problem of deriving quantum mechanics, right? You don't want to derive it now as some sort of effective theory, but you just take it as part of your basic principles. You're working with quantum gravity and not like Einstein was with classical field theory. And this quantization solves ideally, Wheeler hopes, Einstein's problem of stability. Because he argues more qualitatively, just like quantization made the hydrogen atom stable and prevented the electron from falling to the nucleus, similarly, we hope that quantization is going to make these geons or like soliton-like structures in the field stable, and also make sure that certain limitations on their size that we have in the classical theory will be lifted. And so Einstein's program of finding a suitable classical field theory by unifying gravitation and electrodynamics gets replaced by the program of quantizing gravity, with the hope that that's enough. So Wheeler really takes up Einstein's program in a way of reducing elementary particles to field configurations, but he does it by combining that field theory, the field theory of general relativity, with quantum theory, by making the foundation of his proposed theory of elementary particle constitution, or as we would call it now, a theory of everything, by making that based on quantum gravity. And that allows him to take up Einstein's mantle of saying, I'm pursuing this great unificatory program of Einstein himself. He has like a book called Einstein's Vision, right? While not being associated with Einstein's later failures, which were generally viewed as coming from Einstein's rejection of quantum mechanics. And I think that's a strategy that physicists like to use to this day, right? They're saying Einstein's dream was this unification. We're pursuing that, but we understand better than Einstein now that we actually have to work with quantum theory and not try to somehow, ignore it and hope that it'll come out as an effective field theory. And I think Wheeler is really the one to have invented that view. And so we see here his his endorsement of quantum gravity. So you'll see here at the top of the page, this equation, this notebook of a wave function is supposed to be a sum over paths, so a Feynman path integral of the exponential times, and there up there you see the Einstein-Maxwell action, right? And you'll see at the bottom there he's underlined, here's where we start, right? Quantum gravity, that's where I want to start. And a few pages later, he's like, or maybe we should think about unified field theory like Einstein did. But a few pages later, he has like this bronze plaque for this page, as you can see at the bottom. Unified field theories died here, right? And instead now we're talking about quantum gravity, or rather quantum Einstein-Maxwell theory. So including the electromagnetic field in general for him. That is now the foundation for our attempt at a theory of everything, of elementary particle constitution. Okay. So that's how Wheeler arrives at making quantum gravity central to his unificatory and reductionist program. Now we're going to see in the remaining minutes, I guess I have like 20 minutes or so. 15 more like, no?
Look, you are at 30 minutes. We usually ask 30 minutes talks, but we never stop the speaker. So
okay, good. I think okay.
You can take another 10 minutes.
Okay. So what's important to Wheeler is topology change, right? The sum over paths here, that always does not just include metric configurations, but also always topology and different topologies and even dimensionalities. And that's very important, right? He wants to construct charged particles as wormholes, as topological handles with electromagnetic field lines coming out. Here's his first picture of a wormhole in his notebook, which he still calls a woodchuck hole back then. It's important for his vision of the vacuum, where you constantly have a fluctuating topology, and that's what he will come to call quantum foam. And finally, it's very important for him to use topology to endow these particles that are constructed from the underlying field with spin, because that's like his main problem. He knows how to give these particles mass. And he talks about mass without mass, right? Because they're local, localized bundles of energy. But how to also give them spin is a big problem for him. And also there, his hope is that topology change is going to do that for him. So he has he doesn't really work much on the formalism of quantum gravity. It's more like a vision of quantum gravity that's embodied in this path integral, and it's about fluctuating topologies and seeing how that can help us solve problems, help us solve the problem of the constitution of elementary particles. This is not the only vision of quantum gravity, right? And Wheeler's main counterpart is probably this man here, Bryce DeWitt, who has a very different vision of quantum gravity as like the supreme mathematical problem of unifying these two structures without like some big some big goal of a theory of everything in mind, but just putting them together as a mathematical problem and seeing what comes out. It is sufficient, he writes in one of his papers, that the problem of quantum gravity is there, like the alchemist's mountain. Like, we need to do this. There's no need for like a big visionary program like Wheeler's. Now, for some time, these two programs, like the more formalist one and the more visionary one, they can kind of go together, but one does see them clash, I think. Like, for example, here, this is an exchange between Wheeler and DeWitt at the Dallas Relativistic Astrophysics Conference in 1963. We have notes of that from one of Wheeler's PhD students, Dieter Brill. Wheeler is talking about gravitational collapse. And then Bryce DeWitt asks, why not quantize the imploding object, right? Then we don't have to worry about the singularity at the center, because I can get Friedman universe to bounce after down to 10 to the 33 centimeters. And then Wheeler says, couldn't agree more, right? You need quantum gravity, but don't we expect elementary particle phenomena forced upon us? Shouldn't quantum gravity always go hand in hand with talking about the constitution of particles? And then DeWitt answers somewhat exasperated, but it doesn't require anything new, right? Why would you bring in elementary particle problems? All we need to get a big bounce is quantum gravity. So one can see here, for Wheeler, elementary particle physics and theory of everything is an integral part of thinking about quantum gravity, and for DeWitt, it's not. Then comes the equation that ironically bears the name of both of these men. It was mainly DeWitt who constructed it, but Wheeler was very involved in that process and very interested and very much promoted this equation, which he always called the DeWitt equation. For our story, the important thing about the equation is that it's fully based on the classical constraint dynamics, right? There is what we see here is a wave function of three geometries and not of topologies or dimensionalities, right? This equation, which Wheeler refers to as like a quantum gravity reaching a first stage of maturity, right, after initial speculations in the 50s. This does not actually meet Wheeler's expectations for quantum gravity. And while he realizes what an important step it is, and like I said, promotes it very much, which is why it now also calls his name, he's very worried that it does not really fit with his vision for quantum gravity. Again, we can see this in his notebooks. I'm just going to flash one piece here because I think it's very to the point. From January 1967, he's preparing a talk, and he said, in this talk, I should make a comment about topology changes analogous to that which Eddington made about the temperature required for thermonuclear reactions in the sun. When he said, if the center of the sun isn't hot enough, go and find a hotter place because they must take place, okay? And similarly, right, Wheeler believes topology change must take place. And if the Wheeler-DeWitt equation does not include topology change, then he says here again, then we should kick the math to fit the physics and not conversely. So in the beginning, he's not really believing that there shouldn't be any topology change in quantum gravity. But ultimately, he ends with he kind of accepts this and starts looking for new horizons. He really stops working on quantum gravity proper in like really just the formal quantization of general relativity and looks towards new horizons. This is subsumed in an allegorical story that he tells in his textbook with Charles Misner and Kip Thorne. And I'll just read this here. So he says, there are reputed to be two kinds of lawyers. One tells the client what not to do. The other listens to what the client has to do and tells him how to do it. From the first lawyer, classical differential geometry, as embodied for him in the Wheeler-DeWitt equation, the client goes away disappointed, still searching for a natural way to describe quantum fluctuations in the connectivity of space, topology change, as he writes in the margin. Only in this way can he hope to describe electric charge as lines of electric force trapped in the topology of space, wormholes. Only in this way does he expect to be able to understand and analyze the final stages of gravitational collapse. Topology change is really everywhere and central for him. Pondering his problems, the physicist comes to the office of a second lawyer with the name pre-geometry on the door. Full of hope, he knocks and enters. What is pre-geometry to be and say? Born of a combination of hope and need, of philosophy and physics, and mathematics and logic, pre-geometry will tell a story unfinished at this writing, but full of incidents of evolution so far as it goes. So when the first lawyer, which embodies a formal quantum gravity that just quantizes classical general relativity without bringing in new notions of topology change, when that doesn't give him what he wants, he looks to new horizons, and indeed, and we flash this quote again because that's when he goes officially crazy and starts exploring new ideas. We don't really talk about here, but we can talk about them in discussion if you like. I'll come to my conclusions now, which are going to be very brief. So as we've seen, right, it's in the mid-1950s that Wheeler adopts quantum gravity as a potential theory of everything, and really thereby changes the way people think about quantum gravity forever, from like a marginal side problem to perhaps the central problem in understanding the fundamentals of physics. He abandons that again in the 1970s because the formalism for quantum gravity that's emerging encapsulated in the Wheeler-DeWitt equation, does not live up to these unificatory ambitions. And so he goes exploring new horizons in the search for a fundamental theory of physics. And as a summary, we see here that the views on the relevance of quantum gravity have been subject to great historical change. Originally a marginal problem, viewed by some primarily as a formidable technical challenge, it became in Wheeler's hand the great hope of fundamental physics, but at the end also too limited a framework for the vision that he had. So I'll leave it at that, and I'll thank you for your attention, and I'm very much looking forward to questions and comments.
Thank you very much, Alexander. It was a beautiful talk. So I have a few questions, but I will go last. So if you have any questions or comments, you can raise hand or write in the chat. Let's start with Chris, who has raised the hand. Chris Slink.
Hi, thanks so much, Alex. It's a really interesting talk. I was curious about two things with regards to Wheeler's approach. One is, how did he think about nonlinearities in general relativity if you're approaching it from a Wheeler-Feynman approach? And the second thing is, what would he have thought was the framework for a theory of everything in quantum field theoretic terms? So how much was Wheeler keeping pace with developments in quantum field theory, and did his view about how that could be implemented change during this period?
Right. So on the first one, so Wheeler very explicitly says that there would be two possible ways to try and get an action at a distance formulation of gravitation. The one would be kind of starting from general relativity and trying through what he calls a correspondence approach, following Bohr, trying to get an action at a distance theory that mimics general relativity. He's explicitly in the beginning pursuing a different route, and that is to start with what we would expect, what basically just like a relational approach, trying to find possible relations between world lines outside of an actual space-time, and somehow reconstruct possible relations and somehow hope that something looking like general relativity will come out in the end. And that really does not lead him anywhere. He explores lots of things. He's can get like triangles, and can somehow get all of space out of that. But ultimately, he then starts looking into general relativity when he realizes that doesn't work. And then very quickly, he transitions to, oh, well, there's so much to do in general relativity, and it's such a rich theory, especially because of its nonlinearities and results like Einstein and von Hoffmann, that you can, because of those nonlinearities, use the field equations to derive the equations of motion. That he very quickly shifts there. So I mean, ultimately, this is at the time when he's really intensively doing action at a distance gravity, he's not really thinking in terms of nonlinearity at all, because he's just thinking about somehow reconstructing space and time. And as soon as you realize the full potential of the nonlinear field theory that is general relativity, he very quickly swerves towards using those precisely to construct particles. The second question on quantum field theory is a very good one. I think so. My impression is that Wheeler engaged did not engage much with quantum field theory on a very technical level, right? His nuclear physics work and also his early work on metal physics don't really use quantum field theory techniques. So I don't think he really, fully engaged with that. Though of course he does. He is aware of the developments, and they kind of accompany what he's doing. So when he starts with I mean, the whole Wheeler-Feynman electrodynamics is, of course, mainly from Feynman's side, but of course Wheeler plays along with that because it's also kind of more mainstream reason for doing this is to get rid of electromagnetic self-energies in the years before renormalization. And then when renormalization comes along, right, for Feynman, there's just a reason to give up the whole thing. For Wheeler, that kind of shows how we can think about self-energies as something physical, maybe, and he then analogizes in a way the construction of these particles from the fields with electromagnetic self-energies. But so that's kind of, I mean, that's more of like on an analogical level. I think, I give a very streamlined version of his of how that moves away from quantum gravity, but certainly a very important development are the breakthroughs in the early 70s in particle physics, right? These very much impress him. These very much show to him that maybe general relativity is also just not rich enough to reconstruct things like the complicated symmetry structures observed in particle physics. So there, right, and he explicitly says this, right, quantum field theory very much, right, it's not by chance that his program runs precisely through the period of confusion that leads up to the construction of the Standard Model, right? This is the period when he sees an opening for general relativity, and as soon as that period starts to come to a close, and particle physics and quantum field theory seems to have got its act back together, he very quickly also, realizes that, and that's part of his move away from quantum gravity.
Thank you. Okay, if Chris doesn't have a follow-up, we go to Wolfgang.
Hello, hi. Thank you very much for this fascinating presentation. What I found very interesting was this short comment or this remark you had on this exchange between Bryce DeWitt and Wheeler on the possibility that there is a bounce. And could you comment, please, more on that? And perhaps a related question. So, did Wheeler have any specific thought on or vision on singularities, or did they play any, like the Big Bang singularity, the singularities inside a black hole? Did that have the realization that there are such singularities in the theory of classical relativity? Did that have any relevance for him, like the idea to resolve singularities by quantum gravity? Thank you.
Yes, certainly. Absolutely, very much so. Thank you. So gravitational collapse plays a very important role in this story, which I didn't go into in detail. But certainly for Wheeler, but also for DeWitt, I think like one thing that they agreed upon, right, was that the resolution of the singularity in gravitational collapse, or also in a Big Bang or Big Crunch, would be resolved by quantum gravity. It's just that they had very different ideas on how quantum gravity would do that resolution, right? As DeWitt mentions here, right? Here the idea is just, as is, for example, worked out in his 67 paper, in which he introduces the DeWitt Equation, is just basically you get a big bounce, right? So quantum gravitational effects are going to let you avoid the singularity and allow some sort of bounce back. And so there's while for Wheeler also this resolution, like any quantum gravitational result, would have to be connected with the elementary. And would have to be connected with the elementary particle problem. So he was assuming that what would happen in the singularity would again be topology change, universes separating off or whatever. So there was a very different vision of how quantum gravity would affect that, and that, like he says, right, I'm somehow there we go. Back here. It was very much the idea that there would be a connection between elementary particle physics problems and whatever helps resolve the singularity in gravitational collapse, right? Elementary particle phenomena forced upon us, right? We will have to look at have a unified vision. He says, like, if we look at the quantum foam picture, says basically gravitational collapse is happening all the time everywhere in quantum fluctuations. That's why there's an intimate connection between explaining the structure of the vacuum, the structure of elementary particles, and how quantum gravity manages to avoid singularities in gravitational collapse. So that's Wheeler in the 60s, okay? When he still believes in like a quantum gravity program and when we have this exchange. After he then kind of abandons his own quantum gravity particle physics program, he starts propagating a very different vision, namely of gravitational collapse as real, right? And the singularity as real, and really a breakdown not just of a classical theory to be replaced by a quantum theory, but really the breakdown of all physical law, right? It's a much stronger vision of the singularity, of really as the end of lawful physical theories, which he then starts adopting in the 1970s. I don't know, I hope that does that answer the question?
Yes, thank you very much. Thanks.
Okay, there is Terry.
Yeah, thank you. I'm mostly interested in the geometry part of it and this last move to a pre-geometry, and I'm wondering where that went, and particularly whether Wheeler and this whole line linked up to. I mean, Rovelli's now pushing relationalism, and the relationalism ultimately goes back to Leibniz, and there would be some link between those and the development of geometry through that period. And the other one, and I'm wondering, so to focus a little, where did Wheeler go with pre-geometry and in any relationship to relationalism? And then I'm just kind of wondering about Grassmann and what happens when you go into three-dimensional vector calculus.
So Wheeler does not. I mean, so I can't speak about I have not researched the exact lineages from like Wheeler's ideas to contemporary quantum gravity and also interpretation of quantum physics ideas. But I think it seems pretty clear that they were influential there. Wheeler goes in many different directions there. The one that so there's because pre-geometry can mean lots of things for him, right? It can, on the one hand, it goes then in the direction that he then calls it from bits, so somehow having some sort of binary structure of yes/no questions at the basis, where he also exchanges ideas with Carl Friedrich Weizsäcker. But it can also mean, so in the immediate aftermath of this, he goes instead to suddenly, instead of having general relativity as his guide, into elevating the quantum principle and the role of the observer to the central thing, and that is then related to this notion of the participatory universe, where and ideas about the anthropic principle as dictating the laws of the universe. So it's a very wide spectrum there. None of this goes into much technical detail, which of course also makes it somewhat harder to trace the lineages. It's my impression that some of his more programmatic ideas did make quite an impact, but that's something that needs to be researched historically. I'm not sure that I understood your second question about Grassmann. If you could maybe elaborate a bit on that.
Well, and this relates to projective geometry in general, and that tradition goes up to Poincaré and so forth. But Grassmann, and there are others that did this too. There's something you get into variational calculus, and and there's this realization that most of what we did was in planar geometry. And then when you go up into multivariable vector calculus, something funny happens, which you could say is identified with the cross product. And Grossman took it and in a particular way and created this exterior geometry and stuff. But in general, it seems to me that that's one of the core problems in thinking about space-time and geometry. That when you get into multivariable vector calculus, as just reviewing some stuff on this, the guy saying, you need to understand that multivariable vector calculus is not a generalization over the previous. It's something, there's some unique characteristics to it. And if you take that unique, anyway, it's a different, and it's not a metrical geometry. That's one of the issues. You get metrical. The metrical aspect of geometry is that a subcategory, constraints on projective geometry. Projective geometry is everything.
Okay.
I mean, that's where I've been at, and I just don't know whether Wheeler went into that directly. Haven't found anything on
No, so I mean, it's hard to make like blanket statements about Wheeler's thinking, especially looking at the notebooks. Like it explores in lots of different directions, especially in later years. But it is my impression that there is indeed very little geometry in pre-geometry. It's not meant as looking at extensions of geometry or alternative geometries. It is really looking at a non-geometrical foundation of physics in binary, for example, in binary elements, or in anthropic reasoning, or somehow in using purely statistical reasoning, out of which physical laws then emerge. So it's not that he's looking for he is very much interested in questions of generalization of geometry, and especially topology, of course, like I mentioned, in those years from 1950 to 1970. And he's very much in touch, as we can see with his notebooks, also with the mathematicians at Princeton. He very much wants to keep up to speed with the developments in mathematics there. But you can see that that this search for ever new and more sophisticated mathematical structures really subsides then in the early 1970s, where he's convinced that something else, right, in this notion of law without law, right, there is some sort of lawless and not, some lawless foundation to the universe that is not to be sought in more elaborate mathematics, but in, as he sometimes calls it, magic. Yeah.
Can I maybe just ask one more thing? So there's an article of Wheeler's, I think it's either called, it's called Observership as Genesis, or Genesis as Observership, and this is where into the anthropic stuff. And at the end of that, I noticed in the footnotes, he says something like, well, I wrote this, and then somebody pointed out to me that all this had been said before by and I kind of looked at it, it was Schelling. It was going back to Hegel and Schelling, which I don't know where that goes, but I don't know if anybody had any thoughts on that. It just sort of really surprised me that, I mean, that's where Wheeler saw a connection, or he in his commentary saw a connection between where he was going with the anthropic participatory stuff and the Hegelian tradition, so to speak.
Well, I mean, I think indeed Wheeler was interested in these things. One of my PhDs was about a letter where somebody refers to Wheeler, maybe half ironically, as a refined kenner of German idealism. This is I think it's a genuine, though very Wheelerian, which I also think it's not entirely far-fetched. Right? I mean, the Wheeler's this connection to Schelling. Wheeler's idea then that he pursues right after this, like in the immediate aftermath of this, is the idea of putting the quantum principle first rather than geometry. And the quantum principle means for him not any sort of formal structure of quantum mechanics, but means the role of the observer as he takes it from Bohr, who was one of his mentors. Right, he spent a year in Copenhagen as a young man. Wrote, of course, the famous paper with Bohr. He was a big admirer of Bohr. And so he says, he tries to explore whether this role of the observer couldn't serve as a new foundation of physics. And he then indeed comes up with this idea, right, that the universe is only constituted by the fact that it is then observed. So the universe is basically pure potentiality until it manages to create an observer that gives it reality by looking at it. And that is, that is an idea that is that has its relations to German idealism, to Fichte and Schelling, which are also about viewing the world as a projection of the ego in some sense, right? The ego posits the world. So that's it's certainly a not entirely far-fetched analogy, and certainly Wheeler was very eager to pick up these kind. I mean, I'm not sure who told him or who pointed him towards German idealism, but Wheeler was always one to very eagerly pick up these sort of analogies. Always very eager. As the mentioned PhD student Stefano Folan is researching, crafting these long lineages, which are also philosophical lineages, out of which his projects would emerge as the natural outgrowth. So I think it's both it's both a bona fide Wheelerian footnote, and I think it's also there is something to it.
Thank you.
Okay, thank you very much for the exchange. I do not see any other hands. Anybody? No? Okay, I have a question. I'm intrigued by the way you presented the story, which I don't know, but let me see if I get it right in a question. So he initially wanted to follow a program of reduction. So he wanted to get rid of the field. So the way I understand it naively is that somehow you have both the fields and the particles. Can we get rid of one and stay with one type of fundamental entity?
Yes.
All right. Now, so first of all, it seems to me that it's a big cost to pay to go for action at least in order to do this reduction. And do you have any idea why he didn't try to go the other way, which is get rid of the particles, stay with the field, which would make it more obvious how to keep space-time locality, at least naively, from the point of view of today?
Well, ultimately, that's what he did, right? I mean, so indeed that original action at distance program did not work out, and so he adopts an Einsteinian idea of particles as field configurations, though as quantum field configurations. So he then talks instead of starting out as he did with everything as electrons or everything as particles, he then converted. He uses religious metaphors for this to everything as fields. And clearly the central role there is played by the specificity of general relativity, right? Because in classical electrodynamics, the price you have to pay is not that great, right? I mean, there are people who very much like Wheeler-Feynman electrodynamics precisely because it is the only consistent classical theory of charges interacting electromagnetically. But on the one hand, right, as Einstein pointed out when Feynman presented these ideas on electrodynamics in the seminar in Princeton, it's very hard to do the same program with general relativity, and indeed there is less of a motivation to do so because in general relativity, you at least, because it's a nonlinear theory, in principle have the possibility of instead constructing particles from the fields somehow by localizations of field energy through also through the topology with wormholes as a model for particle and so on. So it's kind of a double thing. On the one hand, this action at distance program becomes very difficult in general relativity, right? He does not get anywhere with that. And then also general relativity makes the everything as fields view far more attractive, because you have an angle on how to get particles from it. So the breakthrough is really this in that direction that really leads him all the way from everything as particles to everything as fields, is this this idea of a Kugelblitz, or as later calls it, a geon, where you construct from an electromagnetic wave interacting with its own gravitational field a halfway stable and localized entity, which can be interpreted. He's very proud of this, right? In the paper, he writes that interpreted as the first classical model of a particle, which Newtonian mechanics was still lacking, right? There's no model of a particle, but at best they're somehow points. And well, here you have a model of a particle. So very clearly, I think what you're saying about the large cost of eliminating the field is only partially true, right, in electrodynamics. And there were reasons for him and Feynman to believe that this was a promising way to go, but the cost becomes a lot higher for general relativity. Plus, general relativity also gives you the possibility of actually doing it the other way around because of its non-linearity. So that's why I think, in a way, it's inevitable that given his original idea to do action at distance gravity, together with his reductionist views, he would ultimately end up with the opposite view of everything as fields.
I see. Thank you for the clarification. So let me just insist a bit on that. I'm just surprised, I guess. Of course, it's easy to be surprised with 70 years later, but somehow it's one thing, the cost in the sense of how difficult it seemed to be to actually do this mathematically. The other is I'm just surprised that at that time, because that's quite late in the 40s or whatever, that they would actually put forward the idea that there is actually a distance as a physical, or is this not what they meant? Did they actually have in mind detecting action at a distance, or was this some fiducial thing they have in mind?
Right. So the action at a distance is not instantaneous action at a distance, right? This is always always retarded or advanced action at a distance. So this is always what you would get by integrating out, say, the electromagnetic field. You get these retarded.
I see.
Okay.
So you have Lorentz invariance, but you don't have local degrees of freedom of the field.
That is correct.
Okay.
So what you essentially need for that is what the cost you have to pay is this absorber boundary condition, which is basically that there are enough electrons in the universe that every potential electromagnetic wave will at some point be absorbed, so that you don't have to talk about asymptotic electromagnetic waves, and then you can just do everything.
I see. They try to do away with the radiation degrees of freedom, as we call it.
That's right. Yes, exactly. That's correct.
Chris has raised hand. Please, Chris.
Yeah, I just had a follow-up. I was curious whether Wheeler was influenced by any work on nonlinear versions of classical electromagnetism. So because there are attempts earlier to try to think of particles as stable configurations of the electromagnetic field. Did that have any influence on him, or?
So I'm he certainly sees. All of these are kind of all of these models tend to be in the context of trying to solve precisely the electromagnetic self-energy problem. So basically that you would have infinite inertia if it's a point particle, or would normally be unstable if it's extended. And that's certainly the self-energy problem, and then as it presents itself in QED, that's really where Feynman is very strongly coming from. And that's also the language that that Wheeler and Feynman adopt for the paper. But at the point, right, this is not that essential. He basically thinks that the whole self-energy thing is a red herring, right? And we would be able to do, right, in Wheeler-Feynman theory, we can just think of the particles like pure points moving on lines, right? And self-energy can just be dropped as a term in like the sum of interactions. We can just like drop the self-interaction term. There's no problem with relativistic invariance there, because we don't need to have the field of the electron with which it acts on itself be like the same degrees of freedom as the electron acting with other fields. So I think initially he's just not very interested in this. He thinks it's kind of a non-problem. Then later on, when he then does this pivot that is sketched on this slide here, and really starts thinking about getting extended particles as field configurations, which is preceded also by that's preceded by first thinking about the self-energy of point-like particles. So then he really starts thinking about these things. But the tradition that he sees himself in is already at this point no longer primarily electromagnetic, right? He's already shifted to gravity. He kind of feels, Feynman and those guys, they took care of electrodynamics. That's all taken care of. He's at the frontier of gravitation. So the people he then starts referencing is Clifford. And like 19th century ideas of particles made as lumps of space and time, as he calls them. That's the tradition in which he then places himself, because he already feels he's moved beyond like the electromagnetic worldview pictures or the ideas for dealing with the singularities and electromagnetism. Yeah.
Thank you. That's really clarifies. Thanks.
Okay, thank you very much. This is a good time to close, except if anybody else has some comment or question. Last chance. No? Okay, good. Alexander, thank you very much for the wonderful talk. And yes, hope to see you soon, either in Berlin or Vienna.
Yes, do all apply for the QISS visiting fellowships and come to Berlin.
Yes, good. Thank you very much.
Bye-bye.